Our next presenter is going to be Ranjan Mutia with the City of Fort Worth. Ranjan has been a senior professional engineer with the Stormwater Division of Transportation and Public Works at the City of Fort Worth since 2011. Ranjan has responsibilities for the city's flood warning system and stormwater quality. Ranjan, I'll pass it over to you. Thank you.
Great. Thank you, Jeremy, and thank you for having me over. Hopefully, my voice is carrying over to you all from Fort Worth. Yes? Okay.
Sounds good.
I will. Yep, thank you. So, I'm going to talk about the City of Fort Worth's real-time flood warning system. Appreciate actually talking to you all in transportation, because as you will see, we've had fatalities mainly on roads. So it's great to have a dialogue with you all and talk to you all. So, okay, next slide. I would just want to make a disclaimer about my presentation. If you want to just go back one slide, and I can pick up back. Okay, yeah. So let's pick up over here, same as kind of what Jeremy mentioned. If you can go to the next slide. So just a little blurb on the City of Fort Worth. We are the 12th largest city as of like 2023. We are growing rapidly, and the expectation will actually become the 10th largest city by end of 2025. So we got a good amount of growth. With growth comes more people on the streets. With more people on the streets during a flood event, more people put themselves in flood danger. And so as a result, we also have to grow our flood warning network with the growth past as well as future expected growth. And one of the visions we have is to make Fort Worth a safe community. So the flood safety is also an important part of safety in the city. Next slide. So I just wanted to show you kind of the river network. We do have an extensive river network. Our main river here is the Trinity River. So on the west side, we got the West Fork Trinity River, the Clear Fork Trinity River that joins near downtown and then heads towards Dallas, and that's called the East Fork Trinity River. And in blue, in the blue, you see the city creeks, and then in light brown, you see the even smaller rivers, which also are subject to flooding. And so you can see there's a good dense network of rivers. And whenever there's a significant amount of rainfall, there is potential for flooding citywide. So in the 1940s, the Trinity River had major flooding, and then there was levees built. So as a result, you got sumps built behind the levee network that back up the flows from the creek system. Next slide. So our stormwater utility, which funds my position, was formed as a result of severe flooding in 2004. This was a citizen-led initiative. There was chronic flooding. And then the utility was formed in 2006. The utility is funded by the impervious cover. And we function in 4 main functional areas. We maintain our drainage network, so to prevent clogging and backup. We mitigate flooding hazards through capital improvement projects. So these are expensive projects. And then we also warn the residents through the real-time flood warning network I'm going to talk about, as well as through the floodplain management efforts to prevent people from building in flood-prone areas, and then to prevent people from getting themselves in harm. We also review development so that they don't put themselves or the structures anyway in the floodplain. So you can kind of see some of those pictures at the bottom. Maintenance through the crane at the bottom left. You can see a detention pond in the middle, the flasher network, and you see a roadside flasher on the right, and then our development criteria manual on the upper right side. Next. So a short history, we've had since about late 90s, we've had about 20 fatalities. Nearly all of them have been road fatalities related to floods. And so in 2000 to 2002, we had 3 fatalities that led to 3 test locations. Those were funded by the city funds. Then 2004, we had additional, the one that I referred to earlier, we had more fatalities. We installed a flasher network through city bonds. And then we located these sites based on prioritizing all the hazardous locations. We prioritize up to 285 from 1,500 locations. And then we actually obtained LAPAFA through the Federal Highway Administration, administrated by TxDOT. We added 38 sites. And then in 2018, we upgraded our network from Alert to Alert 2, and also installed dedicated weather stations to have a better understanding of rainfall and intense weather. And these stations were spread throughout the city. And then currently we are installing additional flood warning sites through our own funding. And we are looking at incremental improvements through what we call the road overtop mitigation, HROM effort. So this HROM effort is a way to improve the safety level at as many of these locations as possible by spreading our funding through, making improvements at these flood-prone low water crossings. Next. So here's a listing of the way we went about prioritizing. So we used objective flood criteria, depth, frequency of overtopping, what was the traffic volumes. We looked at past incidents, fatalities, obviously moved the ranking higher, the amount of rescues at a site, resident complaints of flooding. And then we also used how drivers would react as they kind of approach these low water crossings, and incorporated that on a grading scheme. So we used all those grading schemes and ranked the roughly 1,500 sites, and then got to the top 285, and then went down that list and looked at locations where we could install these flood warning systems. Next. So around 2018, we kind of did a reset and kind of looked at our flood warning network and looked at how we could improve it. One of the improvements that we made was to upgrade from Alert to Alert 2. I'll briefly mention that later on. And then also looked at, what do we really need in terms of getting an early lead? And one of the things that we identified is we really need a good rainfall observation network, so we can kind of capture that rainfall intensity as it's occurring, and then also use that rainfall perhaps to nowcast into the future, so we can understand what the flooding would be based off of the rainfall intensity as it's coming in, and then also use that rainfall to bias correct radar products. So that was one of the things that we identified as being one of the missing points in 2018. So we reset it, developed a master plan, And one of the three of the things that we identified was we wanted the system to be reliable, resilient, and then relevant in terms of getting the information out there to the residents, to the driving public as much as possible. And we still got a long way to go on that relevancy part, and we are working hard at it. And I'll provide some information about how we're trying to get the information out to the driving public. Next. So here's a overall design of the flood warning network. Again, a lot of this was done in 2018. So we upgraded to Alert 2, whereas earlier we had one receive site on the left. We upgraded to a secondary receive site so that in case the primary receive site went down, we always had the backup. The secondary receive site, the data was ingested into the cloud server. And then we also have a local server that communicates in the background with the cloud server. On the lower part of the slide, you see what it's like on the ground. We have a master that collects all the local data, the rainfall, the water level as it's rising and lowering with the flood. And that information then is collected by the master and then broadcast out through very high frequency radio, the hydro frequency to the receive sites. Locally, we use spread spectrum to communicate between the master and the flashers to trigger. We also wanted flexibility so that the remote could also act as a gauging station. So we could instrument the remote to collect rainfall as well as collect maybe localized ditch flooding, and then send that information to the master, then the master broadcasts out. So if there's a flood, the master is responsible for letting the remotes know, hey, turn your flashers on, the road's overtopped, and then the flashers would come on, and then they would communicate back and forth as the flood recedes so that the flashers can also turn off. Next slide. Another cartoon of what that looks like. So pretty much repeating what I mentioned, you can see on the left one of these instrumented sites. The conduit goes all the way as much as possible to the flow line of the creek. That was one of the things that we noticed that had to be remedied from the earlier effort. Kind of try to get that water level rising from the flow line of the creek as much as possible. It doesn't always work. You might not be able to access the flow line necessarily, but that's one of the big things. Try to get that measurement continuously as that flood level is rising, so you have early lead up. Okay, next. Here's kind of a depiction of all the different sites. Not going to get into the detail, but you can see, you know, on the right side, upper right side, the dedicated weather stations. One of the challenges in an urban environment, as you can imagine, is trying to find open space so that you don't have obstruction and you have a clean amount of weather measurement of parameters. Sometimes we got to go to the extreme because of theft and vandalism and put fencing around our equipment because there's temptation to cut wires and steal solar panels. So that's something we've had to deal with. Sometimes it happens a little bit more often than we'd like to. And then on the left side, you can see this one over here. If my mouse shows, you can see one of the tipping buckets installed alongside one of the remotes that I was talking to you about so that the remotes can be instrumented as well. Next slide. So if you open the cabinet box, again, I won't get into the detail, but there is essentially a data logger in there that collects the data. The data logger communicates to the telemetry unit, and then the telemetry unit communicates to the radio, and then the radio broadcasts out through VHF. And then the data logger also has inbuilt spread spectrum, so it can communicate to the local remotes. Everything is solar powered, so self-contained. And we back it up with battery power, 35 amp hour battery power. and the batteries are continually monitored through telemetry. One of the things that you see there is a conditioning box. The conditioning box, it just collects, kind of transitions the signal coming out of the pressure transducer and transmits it over to the data logger. The next slide, you will see the next slide. Okay, so next slide is the receive site. This is the alert 2 telemetry. Again, I'm not going to get into too much of it, but it's a significant improvement from the alert protocol. Chris was referring to alert earlier. So alert was whenever there was data collected by the site, it would broadcast it out, whereas alert 2 uses a TDMA telemetry. So each site is given its slot, and then that site communicates within that slot period. We have a 1 minute frame length that's at 60,000 millisecond, and each of the slots is 250 milliseconds. So each site has to collect all the data and transmit within that window whenever there's an event that then is broadcast to the primary and the secondary receive site. The slide you see there is some of the signal conditioning through cavity resonators that clean up that frequency and then send it out through IP protocol. Next. To the cloud server. Here's detailed code and very detailed stuff, essentially consisting of the telemetry unit on the left side, the data logger unit on the right side, and then the data logger unit uses the ports to collect all the data from the sensors that are sending in. There's a lot of performance checking going on in terms of whether any of the sensors are out of compliance, or if there's any issue related to the battery going out of compliance, and there's a flag sent out. So there's a lot of intelligence built into this, and that's one of the benefits of programming, having a programmable data logger. So you can work with the designers and the engineers to customize something that is specific to your needs. Next slide. So this is the same thing. The earlier one was for the master. This is what is in the remotes, a simplified system. But even the remotes, as I mentioned, on the right side, you can have data coming in from sensors, then that collects it, and then the communication is through spread spectrum radio frequencies to the master. Next. So just kind of a menu of the different sensors we have. We have pressure transducers, radars, float switches, rain gauges. We've got distrometers. We measure weather with dedicated multi-parameter weather sensors. And then we also have one site where we have a floodgate that deploys whenever there's a flood. So we have tilt sensors on those. Those have hydraulic tilt sensors as well as MEM tilt sensors on them. Next. So here's a depiction of the multi-parameter. This is actually a Weisseller unit. We measure rainfall through the distrometer. All that is a steel plate that measures the sound made by raindrops or hail. And there's an acoustic signal processing unit underneath that listens to that sound and then translate that into rainfall. And then this multi-parameter sensor also has all the other sensors that you would typically expect from a weather station. Next. Here's what, if a pressure transducer looks like inside, nothing mysterious. This is a contact sensor. It depends on how much that inner membrane plate kind of deflects. And then there are strain gauges that measure that deflection. And whenever you have pressure buildup, that deflection gets more and more, and that signal then varies with that deflection. We use a Keller unit, and these have, again, got to be maintained regularly. I won't talk about maintenance, but all of these systems have to be maintained. Okay, next one. We also use a radar unit. These are particularly useful on bridge decks, and when you have a lot of freeboard from the bridge deck down to the water level. These are great for that. One of the drawbacks is that you need water. It doesn't work too well on dry land. So you need to have the continuous water buildup as the flood is taking place. Next. I think all of you all have seen tipping buckets. So that's another way we measure rainfall. The distrometers are co-located with these tipping buckets, so that's a nice way of checking one against the other. We use the distrometer also as a way of QA/QCing the rainfall. Next. We also, not everywhere, we also use these intelligent devices. This is a Campbell scientific device to monitor the power budget. Very important, especially since we are solar power dependent, to make sure that the power budget is adequate. And you can see in some cases it is the top graph, in some cases it's not in the bottom graph. And so we kind of have to figure out, do we need larger solar panels? Maybe there's tree obstructions and things like that. And all of this is telemetered in real time. Next. So as Chris mentioned, we also use Contrail as our server software. All this information is made available to the public. And then on the right side, you see what it looks like during a severe storm. For the people to see, this is stuff that comes in real time. It'll say avoid if there's a overtop, or caution if the water level is rising, and if there's nothing going on, then it'll just say none. So this is a way for us to get information out to the public. Next. So want to talk to you all a little bit about what happens during a storm event. Lots of complex things go on. So I try to depict that through kind of a cascade diagram. So we do get the National Weather Service notifications prior to the event. Our field crews do routes to check whether any of the culverts are blocked, and if there's blockage, they'll remove it. And then, we also make, if there's a severe event, we also make sandbags available for residents to pick up and barricade around their structures. And then during the event, at least from the flood warning side, there's really not much we do other than just if there is any down sensors. We also have cameras at some of these locations. So we kind of dynamically monitor the situation. If a sensor goes down, we communicate to our field operations to use the camera system in case of need. And then post-event, we run the rainfall report, see what happened, follow up with any of the sensors that may have been down. For example, the recent freeze, we had a recent freeze. Some of those sensors were misfiring. You saw the diaphragm in that PT sensor. If there's freeze, and as you know, water, when it freezes, expands. So some of that can have an impact on those contact sensors, not so much a impact on the remote sensors. And then if there's a severe storm, then we get involved in a more detailed analysis. We sometimes have to debrief council members in terms of the severity of the storm in their particular districts. Next. So here's a couple of things that I wanted to note of things that the first responders get. They do get electronic notifications. We do have code red that we use to notify public of flooding. As I mentioned, the field ops, fire and police have cameras at these low water crossings that they can use to monitor, and you can see some of the pictures. And then fire, these are dynamic things that go on of field operations, barricading roads, and then fire and police responding to 911 calls. At some of the more bigger flood locations, we do have dedicated high water rescue teams that go pre-position in case of rescues that they have to perform. Next. So you see the emails that are sent out on the right side, those two arrows going, as during the rising limb of the hydrograph, those emails are sent out to our first responders. And what we're trying to do, you see on the left side, is using that rainfall to kind of forecast ahead, give them a little bit of a legs up in terms of what could happen in the next 15 to 30 minutes. That's something we are working on right now. But the rainfall information also is broadcast to the first responders, and currently we use the rainfall intensity to give them a heads up in terms of how severe the storm will be. Next. So just quickly, next steps. And I think I'm getting close to running out of time, so I'll go through this next. So what we're doing right now is looking at these low water crossings, developing what we call threshold curves. So this, the question is, what rainfall leads to an overtop? And we are modeling these with HEC-RAS 2D, these low water crossings, developing the threshold, looking at the cumulative rainfall. So the threshold curve is dependent on the rainfall itself. And then we monitor the cumulative rainfall as it's coming through in real time and checking whether it's below or above those threshold curves. And then if it's above, then we know it's going, it's likely to start flooding. And then as that water level starts rising, we also calibrate these threshold, the kind of the dynamic nature of the flood against the water level as it's rising and lowering. And those measurements are coming in real time. And so we are kind of doing this, working on a nowcasting system and trying to look at the rainfall reports as they're coming in, along with the water depth reports as they're coming in, to provide a 15 to 30 minute nowcasting, a look ahead forecast, so that our field ops can get that lead up information. Next. The other thing we are doing, trying to reach out to our drivers through, they do get these, if they sign up, they can get the code red notification, but we're also working on installing these electronic signs at these flood-prone intersections, so that these signages would come on whenever the road overtops, to kind of provide that visual information in addition to the flashes to help them move away from these flood-prone areas. Next. So just to summarize, what are some of the benefits of having these systems? That they provide information to first responders so that they can go and barricade the roads. Unfortunately, the drivers have this tendency, even though they might know the danger, they kind of hesitate, and then they might go through those flooded roadways. So the first responders, if the lead up information, they can use that to barricade roads. If you have systems in communication systems in place, you can reach out to the drivers. You can also educate the residents about flooded roadways, so that they can plan ahead, so that some of these storms might last only 15-30 minutes in terms of the intensities that cause flooding. So if they can just kind of delay what they planned on doing by 15 to 30 minutes, that would just keep them safe. And then the gauges also provide you a good return period analysis in terms of identifying areas that are flood prone. And then going back to that HROM effort I was talking to you about, these flood warning systems serve as an intermediate measure to provide that improved level of safety at these flood prone locations until you can construct expensive projects. And then you can use the data for nowcasting, provide some lead time. And then looking forward, these systems also can be used as navigation tools to help drivers reroute away from flooded areas. Another thing, particularly with some of the cold weather, we're also looking at putting additional road weather sensors, using that infrastructure that we already built out with our flood warning network to host additional road weather sensors. So with that, I apologize if I went just a little bit over. I appreciate the time.